In this lesson, we're going to look at polynomials and kind of their definition. We're going to look at some vocab and just how to do some basic operations, adding, subtracting, multiplying, and factoring polynomials. So some of this may be review for you, but it all ties in together. So we're just going to go ahead and get started here. So first of all, let's talk about some vocabulary. One important word that comes up a lot when we're talking about polynomials is terms. And terms are a very specific thing when we talk about polynomials. And in fact, a term really is synonymous with what we would call a monomial. But term is probably something you're more familiar with. But basically, a term is either a number by itself, so a constant, or a variable by itself, so just an x or a y, or a product of numbers and variables that are raised to any powers. So, for example, we could have x by itself would be a term. 3 by itself would be a term. 3x and 3x squared, and even with a y. These represent products of numbers and variables. So these would all be considered terms or monomials. And we also have certain terms that we would say are like terms. If they have the same variable and that variable is being raised to the same power, we say the terms are like. So, for example, my 3x and x, these would be like terms because they have the same variable that's being raised to the same power. They're both actually being raised to the first power. We just don't write that. It's kind of like also the assumed power there, raised to the 1, is also the same as the assumed coefficient there, which is a 1 as well, if there's no other number written. Which brings us to our next word, which is coefficient. So within a term, the constant or number part is called our coefficient. So for the ones we have above here, the coefficient of this term would be a 1, even if it's not written. The coefficient here is a 3, and it's a 3 here, and it's a 3 here. It's the number part of the term, and generally the number we write out in front. And then a polynomial, so a monomial would be like having one term by itself, like all the three above. Those are all monomials. But if we're adding and subtracting different terms, and they don't have to be like terms, in fact, they would be assumed to not be like terms, because if they were like terms, we would actually combine them together. But if we have a statement that's an addition or subtraction of several terms, we can call that a polynomial. Poly means many. And so if our polynomial has one term, we could be more specific and call it a monomial. A binomial has 2 terms, trinomial has 3, and just generally we refer to anything with more than one term, a polynomial. And when we talk about the degree, this really depends on whether we're talking about the monomial or the polynomial. So when we talk about a monomial, we look at the sum of all the powers within my variables in that particular term, right? Because a monomial is basically a term. So if we're looking up here at the examples I have written here, and we talk about the degree of each one of these monomials, the first one here is a first degree monomial because it has an x to the first power. Right, so normally we wouldn't even have that written, right? We don't generally write that, nor do we write the 1 in front of the coefficient there. But if there isn't anything written, we assume that that's a 1 in its power, so that would be a first degree. The second one would actually be a 0 degree because 3 with no x, we would assume is x to the 0 power, which becomes 1. And we're going to look at that here when we look at some of the exponential rules. If you don't understand that part, just hang on to that. So this would be 3 times 1. So the 3 is a 0 degree. This again would be a first degree. And then this last one here, because I have an x squared and a y, and we assume that y is to the first power, this would actually be a third degree because we take the sum of all those powers 2 and 1. And so that makes it a third degree polynomial. Okay. Or monomial, sorry. When we talk about the polynomials, so I can easily make this whole thing here a polynomial by connecting these with pluses and minuses. And in fact, these two I would want to write together, and we can combine them together by adding their coefficients. Negative 3x and positive x would give me negative 2x. So this would be, okay, so let's look at a polynomial that I have here. It's actually a pretty long polynomial, and if you look through it, there's no like terms. It's all the terms that are like have been combined together. So the first question we ask here is, how many terms do we actually have? And if we want to look at the terms, we want to look at how many of those small pockets of products that we have, right? Or numbers or variables by themselves. So this is one term. This is a product here. That's a variable by itself, a number by itself, a variable to the third power, a product of 4 next to the fourth, and another product. So really what we're looking at is what's being connected by the pluses and minuses. We've got 1, 2, 3, 4, 5, 6, 7. So in this particular case, there are 7 terms in this polynomial. And then what would be the degree of this polynomial? Looking through it, the degree is going to be the highest degree monomial. And the highest degree monomial is this one here. And so this is a 6th degree polynomial. And in fact, many times we would probably write this with the leading, the highest degree term written first. So if I wanted to rearrange this, I can. Be careful, though, about the minuses and the plus. Since I'm subtracting 6x to the 6th, and if I wanted to write this in descending order, I'll write minus 6x to the 6th, because that subtraction, in a sense, makes it negative. And then this would be the next highest term, so minus 3x to the 5th. And then I have an x to the 4th, so plus 4x to the 4th. So notice I'm carrying whatever operation there is with that particular term that is in front of it. And then we have plus x to the 3rd, my 3rd degree term, and then minus 3x squared, that's my 2nd degree term. So I've gotten those, and then plus x and plus 3. So this would be just rearranging it in descending order of degrees. The leading term then is kind of obvious, right? You don't have to do that to figure this out, but the leading term would be the negative 6x to the 6th, and the leading coefficient would be the minus 6. So this is a lot of like symbols and numbers and all these different things. Where do these come from? Well, generally in algebra, these things pop up because of relationships that we observe, and then we create equations to describe those relationships. So here's just an example. So the cost to tile a square tabletop. So number one is the square, where the edge tiles cost $3 per linear foot, and the center tiles cost $2 per square foot. And a bucket of mortar costs $10. So if X represented the linear feet of the square tabletop, let's just say one side of that. So X represents the linear feet of one side of the tabletop. Our cost could be computed as 3 times 4x. Well, where does 3 4x? Well, there's 4 sides. So if x represents the length of one of those sides, then that's one side of a 4-sided square. So it's going to be 4 of those, so 4x, multiplied by the cost per square foot. So if it's 10 feet, that's going to be 40 linear feet, and then 40 times $3 per linear foot gives us the cost for that. And then 2 times x squared. It's $2 per square foot. So again, if let's say it was a 10 linear foot table, that would be 10 squared, or 10 square feet, and the cost is $2 per square foot. So that would be 2 times 100 plus 10, right? Because the $10 is just the cost of the mortar. So this is a polynomial here. We have 2x squared, if we're putting them into descending order. 4 times 3x would give me 12x, and then plus 10. So no matter what the relationship represents, really, we need to understand how to simplify these, and then how to use addition, subtraction, and multiplication, and division. So let's take a look at that. First of all, we're going to look at the adding and subtracting of polynomials, which really is just about combining like terms. When we talk about like terms, for example, I'm just going to do something off to the side here. When I have like 3x, let's say, and I'm going to choose green. What does 3x mean? Well, 3x really, when we talk about multiplication, right, x times 3, this is just a faster way of us doing multiple additions of the same thing. And it's easier to see if we think of it in terms of numbers here besides just variables, because variables are just representing numbers in general. Let's say we have 3 times 2. You guys know that that is 6. Well, the idea behind this, this could represent 2 things. It could be 2 added to itself 3 times. And so the 3 represents how many times it's, how many of the 2's we have. We have 3 of them. But it could also be the reverse, right? We could think of it as 2 3's that we're adding. That would be the same as 2 times 3. Both of these give me 6, right? So multiplication is just a faster way of doing multiple additions of the same number. Okay, so that being the case, if I have 3x and then I have plus 2x, this, remember 3x we could think of as 3 x's being added, x plus x, and then we're adding 2 x's, so 2 x's. Notice that everything here is addition, and so the parentheses don't really mean anything. I could just rewrite this as 5 x's, because that's what we have. So the variable is, the number out in front, the coefficient, is telling me how many of those variables I have being added, right? So I have 3 x's being added, plus I added 2 more x's. The sum total of that is that I have 5 x's being added. So this is what we mean when we say like terms. If it's the same variable following the coefficient, and I have 2 of those that are being added or subtracted, we can simplify them, bring them together, write them as one, because it's unnecessary for us to write them separately. They're describing the same thing being added, right? In this case, they're describing x being added. So as I look at this addition problem, it's one polynomial plus another. I just want to look through and find all of the like terms that I can simplify and add together. And as you're doing this, what you want to think of is the operation in front of it as kind of being the sign of that coefficient, that number, right? So I have 3x to the 4th and 8x to the 4th. Because I have this plus here, and because once you have a plus in between 2 parentheses, we can kind of ignore the parentheses, because it's just one long string of things. With parentheses, we're kind of there just to say, hey, we have 2 polynomials here. But in all reality, we're just, adding a bunch of individual monomials. So we want to look for and add up the ones that are like. So 3 and negative 8 give me negative 5. So I'm going to combine those together as negative 5x to the fourth. I did want to go back here. Notice that I did have an x to the fifth here. These are written in descending order. There is no other x to the fifth. So I'm going to, just keeping this in descending order, I'm just going to rewrite 6x to the fifth there. That's just going to stay by itself because there's no like terms to add together with that. And then we have a minus 4x to the third and a minus 5x to the third. Minus 4 plus minus 5 is minus 9. So minus 9x to the third. And then we have 7x squared and 6x squared. They're both positive, so that's going to give me 13x squared. Then we have a negative 3x and a positive 8x, so that's going to give me a positive. Negative 3 plus 8 is positive 5x. And then we have minus 9 and minus 10, which is going to give me a sum total of minus 19. All right, so this is the sum of those two polynomials. And I'm writing them in descending order, not because it's wrong if I don't, but it's just kind of like one of those things we do. It's like it's to properly express it. That's something we tend to do, just to give it some sort of organizational structure. And also, it's easy for us to identify the leading term, the degree of the polynomial, and all those type of things. Okay, so same polynomials, but now I'm subtracting. So this gets a little more difficult, and you're going to be a little more careful because you'll notice that this subtraction here is in front of the parenthesis. That means we're subtracting not just this polynomial, but each term individually is being subtracted. So even though this is a positive 6x to the fifth, if I'm subtracting it, that makes it negative. And so to clarify this, we want to go through and distribute. I want to make this a plus, even though it started out as a subtraction. And I can do that as long as I change the sign of everything that follows it. And we only have to change what's in the parentheses there. So that becomes negative 6x to the fifth. That becomes plus. This becomes plus. That becomes plus minus. That becomes plus minus. And that becomes plus. And now we can look at these individually and add them up. So again, there's no other x to the fifth term. So this is minus 6x to the fifth. And then, excuse me, a little allergy season here. So then we had 3x to the fourth, and we had 8x to the fourth. That's positive 8. So that becomes plus 11x to the fourth. And then we have minus 4x to the third and positive 5x to the third. So that gives me positive 1x to the third. So I can just write x to the third. Positive 7 minus 6x squared. So that's just positive 1x squared. And then minus 3x minus 8x, that's minus 11x. And then we had negative 9 and positive 10. That gives me plus 1. And so there we have the subtraction. So with subtractions, you always want to distribute and change the symbols. This was a positive 6x to the fifth, so I made it negative. Then I was subtracting 8x to the fourth, so I can just make that minus into a plus. Same here. I don't want to have to erase the addition to write a subtraction, so I'll just put plus negative, right, for anything that was, following a plus. And then every subtraction you can easily just make into an addition. All right. Now we're going to review some of the basic rules of monomials when we multiply them. How do we deal with them? So a few of these, I'm going to give you some examples here, but we'll start off with what's called the product rule. And the names of these I find are helpful to memorize, only because the names are describing what we're doing to the variable in question. So product means multiplication, right? Is the result of a multiplication. So what we're doing with the x here, we're doing with what we would call the base part of the, you have the base and then you have the exponent, but we're multiplying the base. And when we multiply the bases, we end up adding up the the exponents. And I want to kind of demonstrate this here. It's a similar concept to the idea of that powers are a more efficient way or a quicker way of doing multiple multiplications. Just like multiplication was a faster way of doing multiple additions of the same thing, right? So we had x plus x plus x, and this was written as 3x because we have 3 x's that are being added, right? You can also think of it as adding each of those invisible ones that are in front there. That gives me 2x. In a similar way, if we have multiple multiplications occurring, this is x to the third. So the power thing is a more efficient way of doing multiple multiplications of something. So if I have x squared times x to the third, remember x squared is x times x, and then x to the third is x times x times x. And what are we doing between these two? Well, we are multiplying them. So look, it's really just a string of multiplications. And so it's 5x is being multiplied, x to the fifth. So notice that x to the fifth is really just the sum of 2 and 3. By adding up the exponents, we're adding up how many multiplications really are occurring total. So that's the idea here. Between x to the a times x to the b equals x to the a plus b. So for example here, 4x to the third times negative 2x to the fourth. Remember that this is just a bunch of multiplications occurring, right? It's 4 times x times x times x times negative 2 times 4 more x's, right? And in multiplication, we can take things in any order. We can multiply in any order. So with the numbers, we're just going to take 4 and negative 2 and go ahead and multiply that. That gives me negative 8. And then the rest is all x's. And notice that there's 3 of them and then 4 of them. So 3 plus 4 is 7. So negative 8x to the 7th power. I do think it's helpful for us to just point out differences here. When we were talking about adding and subtracting, we could only add or subtract like terms. So if I had 4x to the third plus negative 2x to the fourth, we wouldn't be able to add these together. They're not like, right? And so this is as simple as I could get it. I would just have to leave it like this. But with multiplication, we don't have to have like terms. They don't have to be the same variable being raised in the same power. All we need is just that there's an x there, right? And we can multiply them. Okay, the next rule is the quotient rule, where we have x to the a over x to the b. And so we're dividing, right? We're taking this, we're dividing it by that. Here we were multiplying. Here we are dividing. So product and quotient, those are opposite operations. And so it kind of follows that we do the opposite thing with that power. We subtract them rather than add them. So for this example here, I have 6 x to the 6th over negative 2x to the 3rd. So when we look at the numbers, 6 and negative 2, this is really just division, right? And before, if I had 6 divided by negative 2, you guys would just do that division. And you want to do the same thing here. 6 divided by negative 2 is negative 3. And then we look at our x's, and that's going to be x to the 6 minus 3. So that's negative 3x to the 3rd. 6 minus 3 is 3. So that's the quotient rule, and it kind of follows because products, multiplication and division are opposite operations. We end up doing the opposite things with their powers. Here with multiplying, we added them, and with division and a fraction, we end up subtracting those exponents. All right. The next rule is the power rule. And the power rule, again, we're describing what we're doing to the base or to the variable. We're raising the base to a power. So I'm taking something with a power and raising it to a power. So I sometimes will refer to it as the power to a power rule, just because it's kind of like we're taking this thing that already has a power and we're raising it to another power. But at any rate, what we do with those exponents is multiply them. And let's see how this kind of makes sense, just using some things here. So like if I had x squared and I raise that to the third power, what does that actually mean? This means x squared times itself, right? The base times itself 3 times. And then using the product rule, we can easily see that 2 plus 2 plus 2 is 6. And so that makes sense. 2 times 3 is 6. And so that's what we end up doing with the powers here, is that we multiply them. And don't forget about your numbers either. If I have a 3 here, that cube goes not only to the x to the fourth, but it's also applying to the 3. So that's 3 to the third and x to the fourth to the third. And 3 to the third is 27, and x to the fourth to the third is to the 12th. 4 times 3 is 12. Again, that means x to the fourth raised to the third power is x to the fourth times itself 3 times. All right, the next rule we have is the product to a power rule. And it's kind of a demonstration of what I just did up here. And you'll notice that this power of 3 went to the x to the fourth, and then it also went to the 3 because it was in parentheses. And with exponents, exponents always apply to what's directly in front of them. In this case, what was directly in front of that third power was the 3x to the fourth. So, actually, if I went back here to more specifically kind of illustrate this so it makes sense to you, I should write it as 3x to the fourth, right? 3x to the fourth, 3x to the fourth, 3x to the fourth. So 3, 3, 3, that's 27. 3, 3 is being multiplied. Okay, so in this one down here, I've got 3 to the third again. I've got x squared to the third, so that's going to be x to the 2 times 3, so x to the sixth, and then it's y to the third. So 27, x to the third, x to the sixth, y to the third would be my final answer there. And this applies also with fractions. If a fraction is raised to a power, like we have here, this power applies to the top and the bottom of the fraction. So it's a to the m over b to the m. So we call that the quotient to a power rule. If we're raising an entire fraction to a power, that power goes to both parts of the fraction if there are parentheses there. If there weren't, then we would question whether this a just goes to the m or goes to the b. Because there are cases where we just want it to go maybe to the top number and not to the bottom. So with parentheses there, that means it goes to both. Looking at this example here, this would be, again, 3 cubed, or 27 x to the third over y to the third. All right, and then we have the distribution property. The distribution property you may be familiar with, but whenever we have something times two things that are being added or subtracted, and then we could continue that on. We could have a bunch of additions or subtractions, but a times either of these two, we're going to apply that, make sure that multiplication by a goes to both parts of that binomial. In this case, this is a two-termed, but it could be at 3 or 4 things. The a would be multiplied by each term. So we literally distribute it into that. And this works with real numbers as well. I always like to kind of remind myself, like, for example, we know that 3 times 6 is 18, right? So if we write 6 as a sum, let's just say 4 plus 2, then we want, so all I did was change the form here, right? But we want this to come out to 18. And if we take 3 times 4, that's 12. And 3 times 2 is 6. 12 plus 6 is 18. So this works. And you could do it with subtraction as well. 10 minus 4 gives me 6. So that would give me 30 minus 12. And 30 minus 12 is 18. So any sum or difference you could come up with that ends up as 6, the distribution property will keep that same product going. All right. So in a polynomial, we want to make sure and we take this to every term that's in the parenthesis there. And so this 3x is going to go to both. So that's 3, and then x times x squared gives me 3x's, right? We have x times x squared, so that's 3x is being multiplied. And then we're subtracting 12, and then x times x, which is x squared. And then we have the zero power rule. This is what I was referring to earlier with a different problem. And we're told that anything raised to the 0 power is 1. And there's a couple ways you can look at this to make sure that it makes sense to you. So I always like things to make sense, right? If they make sense, we remember them. And so you always want to go, well, why is that? Can I prove it? Can I show it? And if we look at the quotient rule, for example, let's say we had x to the 6th divided by x to the 6th. Well, for 1, we know that anything divided by itself is always equal to 1, right? 3 divided by 3 is 1. 4 divided by 4 is 1. So if x is just representing a number to a power, and we have 6 of them, and we divide by that, we should know the answer is going to be 1. But also applying the quotient rule, this would be x to the 6 minus 6, which is 0. So we can see that anything raised to the 0 power makes sense that it would equal 1. You can also look at it from just a pattern standpoint. I'm going to give myself some room here. Like if we had 2 to the 3rd, 2 to the 3rd is 8, and then 2 squared is 4. 2 to the 1st is 2. So notice here, every time I'm lessening that exponent by 1, I'm dividing by 2. I'm taking a factor of 2 out, really. So divided by 2. And then we think, okay, well, what should be the next result? It should be this divided by 2. And 2 divided by 2 is 1. So anything raised to the 0 power, we just know is always going to be equal to 1. So 3x to the 0, that's 3 to the 0 as well as x to the 0. And both of those become 1, so the answer there is 1. Okay, and the last thing that we want to tackle here is finding the greatest common factor. And so we want to break down these words a little bit here. Greatest common factor, what exactly does that mean? We'll start with the word factor. Factor is a part, or is defined as the individual parts of a product. So 2 times 3 gives me 6, so we would say 2 and 3 are the factors of 6, or they are factors of 6. So what we're interested here is with the polynomial, it's kind of like when we factor something, we're kind of undoing a distribution. It's like the distribution property in reverse. So there are some ways that we are dividing. So let's look at 2 monomials here. And we're going to look at finding the greatest common factor between these 2 monomials. 3x to the 3rd is 3 times x times x times x. And then 12 can be broken down into 2 times 6 and then 2 times 3. So it's made up of 2 2's, a 3, and that's our 12. And then we have 4 x's, so x, 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 x. when you do something like this, start off with 2 and use it till you can't use it anymore, then go to 3, and you break these down until they're prime. They're numbers that cannot be broken down any further. So 2, and then 3, 5, 7, and 11. That'd be the next prime number. And generally, by the time you get to like 5, 7, or 11, you've gotten all the factors out. So you start with 2, use it till you can't use it anymore, then go to 3, and then if there's anything left, 5, 7, and 11, and then 13 if you need to. But generally, these tend to be the ones that we stop at. Okay, so looking at these two, we say, well, what do they have in common? And you'll notice that we have a 3 in common between them, right? This one has a 3 and the other has a 3. These have 2 2s, but there's no other 2s. So between the two, 3 is the only common factor that they have within the number. And then I've got 3 x's here, and I've got 4 here, so they have 3 in common, right? They only have 3 in common. This one has 4, but this one only has 3. So we can only go as high as the lowest power. So my greatest common factor here would be 3x to the third. That would be the greatest common factor. And so if this was written as a polynomial, like we have here, 3x to the third is my greatest common factor. And so if I want to factor this, that means I want to rewrite this dividing out that 3x to the third. And when I do that, I should rewrite it such that it has the same number of terms as it did originally, right? This is a binomial. There's 2 terms there. And you'll notice that the greatest common factor is actually equal to, in this case, not always the case, but in this case, is equal to the first term, the first monomial in my polynomial. So 3x to the third, if I factor that out, I'm dividing out 3x to the third. That leaves me with a 1, because 3x to the third divided by itself would give me 1. So I'd want to put a 1 there to hold that first place. It's really tempting to kind of think of it as 0, but when we factor something, we're dividing it. All right. With the second term, I had a 12, so I'm taking out a 3. 12 divided by 3 leaves me with a 4. And I took out 3 x's. That leaves me with that single x. So notice what was left when I factored it out was the stuff that was left out of my factoring there. And you should always go, once you factored it, you should always be able to go back, redistribute this, and end up back here, right? So these truly should be equal to each other. Factoring out a greatest common factor means rewriting it. If you started with a binomial, it should end as a binomial in your parentheses. So it has the same number of terms, but you're writing it as a product, right? The word factor is meaning write it as a product. 2 things being multiplied. Write it as a multiplication statement. As what we have here, 3x to the third times this. I've rewritten this statement here, which really is a subtraction. I'm rewriting it as a statement of multiplication. And this comes in very handy to us in future algebraic things that we might want to do. So this becomes an important thing to be able to look for and to do. All right, so looking at this last one here, when I think of the numbers 4, 8, and 2, the largest number that they all share, 4 could be written as 2 times 2, right? 8 could be written as 3 2s, and 2 is just written as 1 2. What do they share? Well, they all share a 2, 1 2. So we can never go higher than your lowest factor there. So since 2 goes into everything, 4 is divisible by 2, 8 is divisible by 2, and 2 is divisible by itself. 2 is my greatest common factor. And then with my x's, there's 2 x's here, there's 3 x's here, and then there's 4 x's here. So what do they have in common? Well, again, we can only go as high as the lowest number that we have. So the greatest common factor in terms of the x's would be x squared. So 2x squared is my greatest common factor. And as I divide it out, 4 divided by 2 is 2. And I took out x squared, so there's no other squareds there. And so we just leave it as 2. There's a subtraction here, so I'm going to leave that. And we took out a 2, so that leaves me with 4. And then we took out 2 x's, that left me with 1x. And we had a plus. The 2 got divided out, so I don't have a number. And I took out 2 x's, so that leaves me with 2 x's here. So 2x squared times this, 2x squared times 2 minus 4x plus x squared is the factored version of this statement of addition and subtraction, this polynomial here. We have rewritten it as a statement of multiplication, so therefore we have factored it.